This video is for Chapter 12, Goodness of Fit Test. In this section, we consider experiments with multiple outcomes. The probability, it is for categorical data. The probability of each outcome is fixed. Definition, a chi-square goodness of fit test is used to determine whether a frequency distribution obtained experimentally fits an expected frequency distribution that is based on theoretical or previously known probability of each outcome. An experiment is conducted in which a simple random sample is taken from a population and each member of population is grouped into exactly one of the K categories. Step 1 is observed frequencies are calculated. Step 2, expected frequencies are obtained from previous knowledge or from a belief or from probability theory. In order to proceed to the next step, it's necessary that each expected frequency is at least 5. That's one of the requirements for this test. There are basically two requirements. The first one, we must have a simple random sample. The second requirement is the data is frequency count for each category and the expected frequency is at least 5. Okay. Hypothesis test is performed. Expected frequency is the mean expected value, so that has to be at least 5. The null hypothesis is always going to be that the expected frequency matches the observed frequency. The population frequencies are equal, so expected frequency and observed frequency are equal. That is always our null hypothesis. Alternative would be expected and observed are not equal. So in alternative hypothesis, we are going to believe that these two frequencies are not equal to each other. They are different from each other. Okay. Alpha is the level of significance. K minus 1 is degrees of freedom, where K is number of categories. So as many categories you have, minus 1 will be our degrees of freedom. And it's a chi-square test. We will be using the test statistic. This is the formula to calculate the test statistic. Summation observed minus expected squared over expected. So you got to have, you're going to do this with every single observed frequency and add those values, and that would be our calculated chi-square. And this is also called a test statistic or calculated chi-square. From alpha and using K minus 1 degrees of freedom, we will find critical value from the chi-square table. Okay, where our goal is to reject H naught if the chi-square, calculated chi-square, our test statistic, is larger than the critical value. It is always a right tail test. This test is always a right tail test. Okay, so I'm going to go through two examples that already worked out. Then we will look at two examples that we're going to do together. Researchers have conducted a survey of 1,600 coffee drinkers asking how much coffee they drink in order to confirm previous studies. Previous studies have indicated that 72% of Americans drink coffee. The results of previous studies are on the left table and the survey from current survey is on the right, are below. At alpha equals 0.05, is there enough evidence to conclude that distributions are the same? So that's my null hypothesis. That's my claim that distributions are still the same. There's no change. There's no difference. So here's the tables given to me. This is from a previous study. This is what was expected. And this is from the current survey. That's what we found out now. So 2 cups per week, there were 15% people. 1 cup per week, 13%. 1 cup per day, 27%. 2 plus cups per day were 45%. And that's from a previous study. Currently, this is what we came up with. So these are our observed values. And these are our expected values. We were expected in our current survey, we expected 15% of the people to drink 2 cups per week. We expected 13% people to drink 1 cup per week. Okay, so the null hypothesis is always H naught, that the expected frequencies or observed frequencies are equal. That means there's no change. Alternative hypothesis would be the null is false, or we can say expected and observed frequencies are different. They're not same. They're different. And we are trying to test this claim, which is our H naught is the claim. Alpha is 0.05 given to me, degrees of freedom. Let's see how many categories are there. So there's 1, 2, 3, 4. We divided people into 4 different categories. So our K is 4 and degree of freedom will be 4 minus 1, which is 3. Now let's go ahead and find out the critical value. So I'm going to use alpha as 0.05 and the row of 3 in the chi-square table. Okay, row of 3 and alpha is 0.05. This is the chi-square table. Row of 3 and alpha is 0.05. Let's see, 0.05 right here. Looks like the critical value is 7.815. Okay, so 7.815 is my critical value. So if I draw, well, that's not a normal distribution. The chi-square distribution is not normal. If I draw the chi-square distribution, so this is a right tail test and my critical value was 7.815. Okay, 7.815 is my critical value. Now I'm going to calculate the test statistic. This one is a little bit of work. You got to use the calculator. R expected, first of all, I need to see how many total number of people are there by adding all of these. Looks like there's 1,600 people if you add them all. Out of the 1,600 expected, so again, this column is for E, expected, were 15% of 1,600. 15% of 1,600, that's what it found in previous study. 15% should have been drinking 2 cups per week. 13% of 1,600 should have been drinking 1 cup per week. 27% should have been drinking. Yes, Alicia.
I'm done playing Prodigy for today.
Okay, good. Thank you. 27% would have been drinking or should have been drinking 1 cup per day, which is 27% of 1,600 is 432, and 45% should have been drinking 1 cup, 2 plus cups per day. So which is 720 people should have been drinking 2 plus cups per day. So these are our expected values based on the previous study. Now we surveyed 1,600 people. This is what we should have gotten in our survey. Now in reality, what did we observe in the survey was actually 206 people drank 2 cups per week, 193, 1 cup per week, 462, or 1 cup per day, and 739 people drink 2 plus cups per day. The next step is observed minus expected. So observed is 206, expected is 240. You subtract observed minus expected. So we do 206 minus 240, which is negative 34. And same, finish this column that way. And then we do observed minus expected squared. I actually go ahead and put the whole thing in my calculator all at once. I just keep on entering. I don't make these columns, but it makes it more organized if you have these columns done one step at a time. Observed minus expected squared. Now I'm going to square the negative 34 and I get that. Square negative 15, I get that. Square the 30, I get that. Square 19 and I get that. Next step is observed minus expected squared divided by expected. And this is what I get in the expected. Observed minus expected squared divided by expected. Chi-square test statistic, if you remember the formula, is summation observed minus expected squared divided by expected. So the last column, if I add them up, that is going to be my chi-square test statistic. So that's how I found the 8.483 by adding all these values. Okay. Now we already found out earlier that the chi-square critical value is 7.815. Does this value lie in the rejection region? So this is my rejection region, all the red rejected region. Does that 8.43483 lie in the rejection region? Yes, it does. So this one, the test statistic lies in rejection region. So this one lies in rejection region. If it lies in rejection region, that means we are going to reject H naught. There is sufficient evidence to reject the null hypothesis that the old percentages are no longer true or old percentages no longer hold. Okay, that's the first example. Here's another example. A department store A has 4 competitors, B, C, D, and E. Store A hires a consultant to determine if the percentage of shoppers who prefer each of the 5 stores is the same. A survey of 1,100 randomly selected shoppers is conducted, and the results about which one of the store shoppers prefer are below. Is there enough evidence using a sigma level 0.05 to conclude the proportions are really the same? Okay, so this is given to me. Notice in this case, I'm not given any previous percentages. Instead, I'm told that out of the 1,100 people, they all like each store equally. That's what they like they prefer 5 stores the same. Okay, that means they all liked 11 each store in the same proportion, same number of people like each store out of the 1,100. Okay, so our null hypothesis is the population frequencies are equal to the expected frequencies, or we can say the same number of people like each store. That's okay as well. Alternative hypothesis is the null is false, or we can write not the same number of people like each store. Not the same number of people like each store equally. And alpha is 0.05 degrees of freedom. We have 5 different categories here. We have stores, 5 different stores. So 1, 2, 3, 4, 5. Degrees of freedom would be 5 minus 1, which is 4. And alpha is 0.05. What is my chi-square critical value? Critical value in this case is going to be, so 0.05 is area to the right. I'm going to look in the column of 0.05, but the row of 4. Okay, let's check. 0.05 in the row of 4. Looks like it's 9.488. All right, so 9.488 is my 9.488 is my critical value. Okay, let me write a little better. Than 9 does not look good at all. 9.488. Next, I'm going to calculate the test statistic. We saw the formula earlier for the test statistic is observed minus expected squared divided by expected, and we got to find sum of that column. So if 5 different categories are there and people like the store equally, that means 20% of the people like store A, 20% of the people like store B, 20% of the people like store C, 20% D, 20% E, because that's how 100% of the population would equal, we can divide it in equal number of, out of 1,100, 20% people would have liked the store A. So 1,100, 20% of 1,100 is 0.2 times 1,100, which is 220. And that should be same for every single store. So out of the 1,100 we surveyed, 220 should have liked store A, 220 should have liked B, 220 should have liked C. But in reality, this is what we observed. The purple column is what we observed, and the red column is what we were expecting. And the next column is observed minus expected, 220 minus 262. And then we square these values and then divide by the expected again. And if I find sum of this column, that is going to be my chi-square, calculated chi-square. This is also called the test statistic, calculated chi-square. And that's 14.618. Does that 14.618 lie in the rejection region? Yes, it does lie somewhere in the rejection region. If it lies in the rejection region, that means we're going to reject H naught. If we reject H naught, there is sufficient evidence to reject the null hypothesis and to believe the customers do not prefer each of the stores equally. Okay. Now I'm going to go to the supplement. I will be working on page number 272 of our supplement. So let's check that out. Page 272 is here. That's chapter 12. It is test on categorical data, inferences on categorical data. So we're using categorical data, not the numerical data anymore. It's an attribute, not the quantitative. It's a qualitative data. Okay. So goodness of fit test starts on page 272. Goodness of fit test is used to, again, a quick review, determine whether a population has certain hypothesized distribution expressed as proportions of individuals in the population falling into various categories or various proportions. There are two types of goodness of fit tests. One type might say there's equal proportions, like the second example we saw. The second kind might actually give you some proportions from the previous study that we want our current proportions to match. Okay. O stands for observed frequency, expected frequency. K is the number of categories. N is the total number of sample values. Requirement, simple random sample. Data is the frequency count for each category. And expected value is at least 5. Expected frequency is at least 5. H naught will be always the frequency count agree with the claim distribution, or it would be all groups are equal. H1 will be that the null is not true. So we're going to say opposite of the null in H1 in alternative hypothesis. Test statistic, this is the formula to calculate the test statistic. Degrees of freedom is K minus 1, where K is the number of categories. So that is not OD, it is OF, number of categories. Okay, I'm going to make that correction. Number of categories minus 1. If calculated chi-square is greater than the critical value, we reject H naught. If calculated chi-square is smaller than critical value, we fail to reject H naught. If we reject H naught, there is sufficient evidence. If we fail to reject H naught, there is insufficient evidence. If all categories are equal, expected value would be N divided by K. If all categories are not equal, then expected value would be N times P. It is always a right tail test. Let's check out an example together. A vending machine has 5 different beverages. The salesman of machine says that all kinds of drinks are equally favorite among people. His manager wonders if it is true and observes what people get out of the machine and records the results. At alpha equals 0.05, test the claim if salesman is correct. Okay, and there's no values given. Actually, there is something missing here. So I need to fix that. And I'm going to be giving you the values now. Because without giving you any data, we cannot perform this test. Okay, so the data is drinks. And then number of people or frequency. The drinks are Coke, Pepsi, Sprite, Dr. Pepper, and iced tea. Sprite, Dr. Pepper, and iced tea. Okay, so we have 52 people who took out Coke, 63 people took out Pepsi, 25 people took out Sprite, 59 people took out Dr. Pepper, and 48 people took out iced tea. Okay, let's go ahead and set up our null and alternative hypothesis. Null is all drinks are equally favorite. All drinks are equally favorite, so same number of people grab each drink. And the alternative will be all drinks are not equally favorite. Okay, our expected value, now in this case, if you notice, it says all the categories are equal. Expected value is going to equal total divided by number of categories, So out of the total number of people we observed, if I add 52 plus 63 plus 25, so 52 plus 63 plus 25 plus 59 plus 48 divided by 5, and that all came out to be 49.5. Okay, that's 49.5. 247 divided by 5. Let me double check my calculations. So we have 52 plus 63 plus 25 plus 59 plus 48. 247 divided by 5 is 49.40. Okay, so that's 49.4. I'm just writing as 49.5 because it's easier to do the calculations with 49.5, but it's actually 49.40. To be more, let's just make it correct, 49.40. Okay, 49.40 is the correct 49.40. Okay, 49.4. All right, let me write 49.4. All right, so now I'm going to go ahead and calculate the test statistic, and that is a lot of calculator work. You also grab your calculator and do summation observed minus expected squared divided by expected. Okay, so I'm going to grab a calculator. I'm going to do each observed. So observed, I have 52 minus expected was 49.4 square plus 63 minus 49.4 squared plus, you keep on going that until your last value and divide by expected. In this case, each expected was equal, so I'm just writing it as a single fraction, but you can write them as separate fractions as well. Okay, if the expecteds are not all equal, we cannot write them as a single fraction. All right, go ahead and do this calculation and we will match and check in a minute. I got 17.83 as my test statistic. 17.83 is my test statistic by doing all the calculation. So I am ending up with 17.83. Okay, so 17.83 is my test statistic. Let's go ahead and find the critical values as well. To find the critical values, we would look at the degrees of freedom. Here in this case we have 4 degrees of freedom is 4, and alpha given, yes, it's 0.05. So that would be same as the last problem because we did use degrees of freedom 4, and so 9.488 is my 9.488. Okay, nope, I'm on here. All right, 9.488 is my critical value. So chi-square critical value is 9.488. 9.488. Now that test statistic does lie in the rejection region, so we're going to reject H naught, and we're going to say at alpha equals 0.05, there is sufficient evidence to reject the claim that all drinks, that all drinks are equal favorite, claim that all drinks are equally favored. Okay, we're gonna look at one more example, and then for the homework we will be using technology StatCrunch. I will be showing you how to use the StatCrunch as well for the homework. The next example we're looking at, let's see. Forest Service surveyed Sacramento area in 1970 and determined that 60% of land was in pristine condition, 20% was in good condition, 15% was average, and 5% was poor. They just did the survey on 200 acres again and to see if the land conditions have changed. So our null would be land conditions are same. Land conditions are same, and H1 is land conditions have changed. Okay, have changed or not the same, however you want to write it. So we are trying to figure out our, first of all, we want to figure out our observed count and the expected count in this case. So they did on 200, let's see, what was observed in the past? Observed, so how much was pristine, how much was good, how much land was average, and how much land was poor. So observed, we observed 100 acres were pristine, 45 were good, average were 35, and poor were 20. What was expected? So earlier 60% was pristine condition. How many acres should have been in pristine condition now? So what is 60% of 200? 60% of 200 is 0.6 times 200, that is 120. 20% should have been in good condition. 20% of 200 is 40, and then 15% of 200 is 30, and 5% of 200 is 10. So we have our observed and expected frequencies. The next step, you can do the critical values first or the test statistic first. I'm going to go ahead and do the test statistic first. So to calculate the test statistic, I need to do chi-square is equal to summation observed minus expected squared over expected. Okay, so each observed, which is 100, minus expected is 120 squared divided by 120 plus observed minus expected squared divided by expected plus 35 minus 30 squared divided by 30 plus 20 minus 10 squared observed minus expected squared divided by expected, and that all turns out to be 14.8, and that's my chi-square test statistic. Let's look at the critical values now. Critical values are solely based on the alpha. StatCrunch will be asking for MyMathLab will be asking for p-value. It's impossible to find p-value, exact p-value from the chi-square table most of the time. So we're going to be able to get it from the StatCrunch. I'll show you that in another video. Okay, so critical value is going to be based on alpha. Were we given alpha here? 0.05. If it's not given, always go with 0.05. And degrees of freedom in this case will be 3 because there's 4 different categories. So let's go ahead and find the chi-square value with alpha 0.05 and degrees of freedom 3. That turns out to be 7.815. Now, does the test statistic lie in the rejection region? Yes, it does. So reject H naught. If we reject H naught, we're going to say at alpha equals 0.05, there is sufficient evidence to reject the claim, sufficient evidence to reject that the land conditions are same. To reject, okay, pencil, reject that land conditions are same. Land conditions are same. Okay, that would be end of goodness of fit test.